Every year, over 1 billion gallons of paint are produced worldwide, enough to cover the entire area of the US 10 times. But how is paint capable of withstanding the heat of Dubai and decorating skyscrapers like the Dubai Creek Tower, born from crude oil? This isn't just a solution in pigments. It's a symphony of pipes, reactors, and ultrasonic checks, where precision is more important than a milligram. From the oil refining column to robotic arms that carefully package each can. And if you watch this video until the end, you'll learn one little known fact that paints the entire industry in new colors. Tankers of oil are drained into separation tanks. Here, at a height of about 60 feet, stands the fractional distillation column, a labyrinth of pipes and valves that transforms boiling liquid into a stepwise separation of hydrocarbons. Vapor rises through mesh trays with intervals of 10 inches, each of which filters out a separate fraction by its boiling point. At about 350 degrees Fahrenheit, kerosene is separated, then diesel, lubricating oils, and closer to the top, light aldehydes and aromatic hydrocarbons, which will later become the basis for the chemistry of polymer paints. After fractional distillation, each selected fraction is directed to the reactor hall through a network of high-precision pipelines that stretch for tens of yards along a technical corridor. The pipes are made of hardened steel, 4 inches in diameter, with an inner Teflon coating that prevents corrosion and chemical wear. The flow of fractions is regulated by electronic valves that react to real-time temperature and pressure readings. Each section of the pipes is equipped with sensors that read the liquid's viscosity, impurity level, and delay time at filtration nodes. Booster pumps with ceramic rotors pump the fractions at a speed of 15 gallons per minute, preventing turbulence, so that the molecular structure doesn't change. At turns, the pipes are enclosed in cooling jackets that maintain the temperature within 120 degrees Fahrenheit. Finally, before entering the reactor hall, the components undergo a final check, using a spectrometer installed directly in the injection unit. The flow pulses evenly, like blood in vessels. Precision and rhythm here mean the quality of the paint that will take on the desert sun. In the industrial zone, the temperature reaches 600 degrees Fahrenheit, and the air is saturated with the smell of toluene and benzene. Here, the first stage of synthesis begins, cracking and alkylation. Huge reactors, resembling vertical steel barrels 20 feet high, mix the components under a pressure of 60 psi. In 8 hours, these compounds change their structure, acquiring the properties of polyurethane, the basis of a durable paint for exterior coatings. Filtration occurs through tubular separators with titanium membranes less than an inch thick. They are capable of passing only molecules of a certain size, filtering out residues of unwanted reagents. The hot mixture, which has just passed through reactors, filters, and pigment mixers, enters the packaging sector. Here, under the control of sensors and robotic manipulators, the paint is poured into 5-gallon steel containers, a standard that allows for easy transport and storage of the material on skyscraper construction sites. The containers are not just cans. They are made of chrome-plated steel, with an internal anti-corrosion coating that withstands the aggressive chemical components of the paint. Before filling, each can undergo a preliminary leak test. Laser sensors scan its surface, and robotic grippers rotate the container at various angles to detect deformations. After this, the paint is poured through injection heads that control the volume with an accuracy of 1/100th of a gallon. The mixture temperature is about 100 degrees Fahrenheit, which ensures optimal viscosity for pouring. Filled cans are transported by conveyor to the polymer sealing shop. Here, one of the most important stages takes place: ultrasonic inspection. The cans enter chambers where high-frequency waves pass through the metal shell. Sensors detect any structural violations, microcracks, air pockets, weak welds. If a defect is found, the can is automatically rejected from the line and sent for reprocessing or disposal. Those that pass the inspection move on to the marking station. Here, laser printers apply a heat resistance index, production date, mixture code, and also a QR code to the can's surface, which allows for tracing the entire production history. from the oil field to the specific reactor. In some cases, an RFID chip is embedded in the lid, providing digital identification at the construction site. When the cans of paint have passed all stages of inspection, marking, and sealing, they enter the logistics zone, a place where engineering precision turns into a choreography of transportation. Here, in the loading shop, 5-gallon steel containers are placed on pallets, 48 pieces on each, taking into account weight, center of gravity, and stability. The pallets are wrapped in shrink film, which protects the cans from dust, moisture, and mechanical damage. Then they are marked with RFID tags, which allow for tracking each unit in real time. Automated forklifts, electric machines with laser navigation, pick up the pallets and transport them to the loading platforms. Here stand trucks with thermally insulated bodies, equipped with temperature and humidity control systems. In Dubai, this is critical. The paint must not overheat or cool below 60 degrees Fahrenheit. Otherwise, its structure will change. Before loading, each truck is scanned. The cleanliness of the body, the tightness of the doors, and the functionality of the cooling system are checked. Loading takes place via hydraulic platforms that level the height of the truck body with the warehouse level. Robotic arms, equipped with pressure sensors, carefully place the pallets inside, following a placement scheme. Heavy, closer to the axle, lighter, to the doors. After loading, the system automatically records the position of each pallet, updating the route in the logistics database. The trucks set off for the construction sites of skyscrapers, for example, to the Dubai Creek Tower or Wanza Abail. On the way, each truck is accompanied by GPS monitoring, and the driver has a tablet with temperature updates inside the body. If the indicators go beyond the limits, the system sends a signal to the central server, and the cargo is redirected to a backup warehouse. On site, the paint is unloaded using mobile cranes or elevators if the construction is already at a height. The cans are lifted to the floors where painters in heat-resistant suits are working. And when the first stroke is applied to a concrete panel, the final act begins. The paint, which has traveled from oil to pigment, becomes part of Dubai's architectural canvas. In the US, the paint market is valued at over $34 billion, with over 1,003 million gallons of paint produced annually. In the UAE, about $100 million and significantly smaller volumes, but with a high share of exports. In the US, over 300,000 workers are employed in the paint industry, while in the UAE, the market is more automated and less labor-intensive. Both countries are moving towards environmental standards. In the US, paints with low VOC content are popular, and in the UAE, nanocoatings with thermoregulation. The Jotun Company has plants in Abu Dhabi and Dubai, and National Paints owns one of the largest paint production complexes in the Middle East. In 2025, the Jotun Company continued to show stable growth. In the first 4 months of the year, its operating revenue was over $1 billion. This is 4% more than in the same period of 2024. The company employs over 10,600 people, has 67 subsidiaries, and 40 production facilities worldwide. Exports to the US account for less than 1% of total sales, which reduces risks associated with tariff changes. What information impressed you today? Every year, over 90% of all copper alloys ever created are recycled worldwide. The story you are about to see is not just about bronze and brass. It's about metal alchemy, where old pipes and worn-out tools are reborn as gleaming ingots, musical cymbals, and even ship propellers. How does ordinary plumbing turn into cathedral bells? Why does a metal foam in the furnace save the alloy's quality? And most importantly, what secret does the white smoke rising above the foundry hide? Watch until the end, and you'll find out something most people don't even know. First of all, what's on our menu? The main characters of our story today are two noble alloys, bronze and brass. Bronze is like a solid, respectable gentleman in the world of metals. Its base is copper, with a bit of tin added for company. This duo is so successful that it gave its name to an entire historical era. Sometimes, other guests, like zinc or lead, join this party to give bronze special properties. Brass is its sunny, cheerful, and slightly audacious sister. It also starts with copper, but instead of tin, its best friend is zinc. It's zinc that gives brass its bright, golden color, reminiscent of a sunbeam. And where do all these components come from? A large portion of the raw material consists of recycled heroes. Old plumbing pipes, worn-out faucets, unwanted wires, and even shiny but retired musical instruments. All of this goes not to the landfill, but for rebirth. A bit of pure copper, tin, or zinc is added to them to get the perfect chemical cocktail. When all the ingredients are gathered, the hottest stage begins, melting. Imagine a giant cauldron, a real jacuzzi for metals, heated to temperatures that the sun can only dream of. This is a melting furnace. Most often, it's an induction furnace, which uses a powerful electromagnetic field to heat the metal from the inside, causing it to melt quickly and evenly. The loading process is similar to making soup. Operators, like master chefs, carefully pour scrap metal and pure metals into the red-hot belly of the furnace. It's so hot that if you threw a snowball in there, it would evaporate before it even realized what was happening. But just melting the metal is only half the battle. In the molten mass, as in any company, there are unwanted guests, impurities and oxides. To get rid of them, a special substance is added to the melt, flux. It's like a bouncer at our metal party. It finds all the contaminants, gathers them together, and pushes them to the surface in the form of a foam called slag. Then, an operator takes a long tool, similar to a huge spoon, and carefully removes this slag, like foam from a morning cappuccino. Now our liquid metal is clean and shiny, but is it perfect? To check, a lab technician takes a small sample of the melt and takes it for analysis to a spectrometer. This smart device tastes the metal in a few seconds and provides its exact chemical composition. If something is missing, the necessary ingredient is added to the furnace, bringing the alloy to perfection. When our metal soup is ready, the most spectacular moment arrives: pouring. A stream of liquid sun, a dazzling waterfall of gold, is poured from a huge ladle into molds. These molds, or casting forms, are essentially beds for the future ingots. They are usually made of thick cast iron, or graphite, and have a simple elongated bar shape. Before accepting the hot embrace of the liquid metal, the molds are necessarily preheated and coated with a special coating. This is done so that the metal doesn't get a cold shock and doesn't stick to the walls, and the ingot comes out smooth and beautiful. Pouring requires a steady hand and skill. The operator slowly and smoothly tilts the ladle, filling one mold after another. Now it's time for our ingots to take a little nap and gain strength. The liquid metal in the molds begins to cool and solidify, turning from a liquid into a solid. This process proceeds from the walls to the center. When the ingots have solidified enough, but are still very hot, it's time to wake them up. A worker, using a special tool, or simply by striking the mold, knocks the finished ingots out. They fall to the floor with a loud metallic clang, glittering in red and orange colors. They are still very hot, so they are either left to cool in the air, or if the process needs to be sped up, they are submerged in a large pool of water. This immersion is accompanied by loud hissing and clouds of steam. A real water show. Finally, when the ingots have completely cooled, it's time for the final touch-ups. Sometimes, a small burr remains at one end of the ingot. This is the solidified metal from the channel through which it was poured. This tail is carefully cut or broken off with a hammer. Then each ingot undergoes a final inspection. An inspector checks it for cracks, voids, or other defects. If everything is fine, a mark is stamped on the ingot. Its personal passport, indicating the alloy grade, batch number, and weight. Now they, shiny, heavy, and perfectly straight, are stacked in beautiful piles, ready to go out into the big world. They will be made into new faucets, beautiful door handles, musical symbols for drummers, parts for ships, and even majestic monuments. Thus, the journey from a pile of old scrap to a shining ingot is completed. And isn't that real magic, seasoned with fun and fire? The applications for these alloys are diverse. In plumbing and construction, brass is used to make faucets, valves, and fittings due to its corrosion resistance. In marine applications, bronze dominates due to its exceptional resistance to corrosion in salt water. It is used to make propellers, pumps, and ship hardware. In electrical engineering, brass is used to produce terminals, contacts, and sockets. In mechanical engineering, bronze and brass are used to make parts that operate under friction, such as bushings, plain bearings, and gears. Practically 100% of all bronze and brass products can be recycled without loss of quality. About 90% of all copper alloys ever produced are still in use thanks to recycling. The use of scrap metal for the production of these metals saves up to 85% of the energy compared to production from primary ore, which significantly reduces carbon dioxide emissions and the load on deposits. Have you ever seen old bronze monuments covered in a beautiful greenish-blue patina? That's not rust and not a sign of decay. It's a patina, a protective film that forms on the surface of copper alloys under the influence of air and moisture. The most famous example is the Statue of Liberty in New York. Initially, it was a bright copper red color, like a new penny. But over the decades, the ocean air created a strong layer of patina on it, which not only gave it its famous color, but also protects the metal underneath from further corrosion. Today, many artists and architects even artificially age their products to immediately get this noble coating. Why are bells and orchestral cymbals cast from bronze, and trumpets and saxophones from brass? It's all about the unique crystal structure. Bronze has the ability to vibrate for a long time and cleanly without absorbing sound waves too quickly. When a bell is struck, the sound doesn't die immediately, but rolls on, creating a rich and lasting hum. Brass, on the other hand, is more ductile and easier to work with, which allows for the creation of complex shapes for wind instruments, and its sound is brighter and sharper. So, when a foundry worker pours the metal, he is essentially casting not just an ingot, but a potential sound, a future melody or a solemn peal. When melting brass, an interesting and somewhat dangerous phenomenon can be observed. Zinc has a much lower boiling point than copper. Therefore, when the alloy is heated to the melting temperatures of bronze, the zinc begins to actively evaporate. Its vapors instantly oxidize in the air, forming a thick white smoke that looks like wool. This is zinc oxide. Experienced foundry workers call this the burning of zinc. Inhaling this smoke can cause a specific condition similar to the flu, with chills and a headache, which is called metal fume fever. Therefore, good ventilation in a foundry is not a whim, but a vital necessity. Every year, over 100 million cubic meters of plywood are produced worldwide. That's enough to cover every roof in the United States with a whole tree. But few people know how this journey actually begins. Imagine, a wet log, still smelling of the forest, enters steaming chambers, passes through steam, knives, fire, and a pressure of 250 psi to become a wall, a roof, or even a stage. How is a log transformed into plywood that will last for decades? And what secret does the peeling process hide? If you watch until the end, you'll discover what they don't write in textbooks. The factory wakes up before dawn. With a deep roar, the gates open and trucks with freshly cut logs slowly drive onto the site. You should see them. Oaks, pines, poplars, true forest giants, long, thick, heavy, with wet bark and the aroma of a freshly felled forest. The wood is still breathing, still warm from the sun that shone on it for the last time. And so it begins. The logs are dumped onto a hydraulic feeder, where they move like logs in a mountain stream. Only instead of water, a system of rollers and chains is at work, and instead of a river, washing chambers, loud and ruthless. Bam! A jet of water under a pressure of 1000 psi, almost like a fire hose, hits the wood from all sides. All the mud, dust, and pieces of bark are torn off, like old skin. The logs spin, collide, foam, and hum. It looks as if the wood is undergoing a purification ritual before becoming something greater. After such a washing, they shine. But that's not enough. The wood is strong, rigid. You can't peel it like butter. So next, the steam chamber, a real wooden spa resort, but on an industrial scale. The logs drive onto an overhead crane, are lifted, and slowly submerged into giant cylinders, steam vats 60 feet long. And there, behind closed steel doors, begins what engineers call fiber softening, but I would call it wood stewing. Inside, it's 220 degrees Fahrenheit. The steam is thick, saturated. For 8 or even 12 hours, the logs soak in this environment. The steam penetrates to the core, the fibers relax, the resin starts to flow a little. And if you listen closely, it's as if you can hear the wood sigh, as if admitting, "Okay, I'm ready, make me into plywood, make me." They are taken out, and the logs are no longer the same. If at first they crackled with tension, now they are flexible, elastic like wet towels. Steam still billows from the bark, wood chips remain on the floor. The smell is like a sauna in the forest after a rain. They are stacked on roller conveyors and prepared for the next step, peeling, where they will lose their wooden identity, but acquire a new one. The log, fresh from the steam bath, is still smoking, as if someone just threw it from a pot onto the cold concrete. It is grabbed by a mechanical clamp, huge, like a transformer's paw, and lifted to the peeling machine. A giant with a steel mouth that is already humming, like a Harley-Davidson's engine at full throttle. This machine is a centrifugal peeling line, or simply put, a shredder. The log, heated and pliable, is mounted at the center of rotation, like a kebab on a skewer. It begins to spin slowly, then faster, even faster. And here the peeling knife comes into play, long, straight like a samurai sword, only made of steel and as wide as the entire log, 4 or 5 feet. And it doesn't cut. It peels, layer by layer, strip by strip. Screech! Shh! Vroom! The log spins, and a thin, flexible layer of wood comes off it, only 1/16 of an inch thick. It unfurls like a gift wrap ribbon, only instead of glitter, there's warmth, steam, and the smell of fresh wood. And instead of music, the roar of hydraulics and the rhythmic rustle of the plywood roll. This ribbon is veneer, the basis of plywood, its soul. It comes out without stopping, tens, sometimes hundreds of feet long, is rolled up or automatically cut into large sheets, typically 4 by 8 feet. Peeling is a sensitive process. The log must be straight, symmetrical, moist, but not too soft. If it cracks, it's over. The veneer will have holes or waves, and the plywood won't be grade A, but oh no. Operators carefully monitor every movement. On the display, graphs of speed, pressure, layer thickness. Cameras capture every knot. If something goes wrong somewhere, the machine stops in a second. And then they fix it, readjust it, and back to the fight. When the log is exhausted to the core, what remains is a core, a few inches thick. It's automatically ejected to the side, to be later processed into sawdust, fuel, or wood chips. Nothing is wasted here. Everything will be used. And the veneer sheets, hot, pliable, still smelling of steam, race onto the dryer. But for a moment, as they come off the knife, they are incredible. This is living wood, which has already lost its tree form, but has not yet become plywood. It flows like water from a tree. It dances like a gymnast's ribbon. It rustles like paper, but carries the strength of a trunk. As soon as the veneer ribbons come off the knife, they are still damp, steaming, like leaves after a thunderstorm. And so, they are picked up by an automaton, pulled into a drying line, incredibly long, like a train in Texas. Inside, hot air, about 200 degrees Fahrenheit. Flows are accelerated by fans. The sheets race along a conveyor belt at a set speed. 10 or 15 minutes, and the veneer comes out dry as a bone. and at the same time, still flexible, because if you over-dry it, it will break like a chip, and if you under-dry it, the resin won't stick later. Everything, down to the micron, down to the second. It's not just automation at work here, but also the intuition of the dryer operator, who can tell by sound and smell. This oak is still damp. Next, sorting. Veneer sheets, dozens, hundreds, roll onto an inspection platform, where operators or modern cameras with artificial intelligence decide where each should go. A sheet without knots, perfectly even, goes for the face layer, the highest grade. With small cracks, to the middle, with large defects, into the inner layers, or for backing. Everything that doesn't fit is shredded and sent for recycling. Nothing goes to waste. The selected sheets are fed to glue applicators, huge drums that evenly roll on a waterproof phenol formaldehyde resin. It's dark brown, thick, sticky, smells sharp, like a school desk after woodshop class. And here, everything is important. The layer of glue, the temperature of the sheet, the direction of the fibers. Because plywood isn't just glued sheets, it's cross-laminated layers, where each layer runs perpendicular to the previous one. This is how it gets its mechanical strength, flexibility, and resistance to warping, like a bulletproof vest, but made of wood. The finished sandwiches of several layers are placed in a giant hydraulic press that applies pressure from 150 to 250 psi, at a temperature of about 300 degrees Fahrenheit. Inside the press, it's hell, but a controlled one. 10 minutes and the resin hardens, binding the fibers into a single body. The plywood becomes monolithic, hard, sanded from the inside out. This moment is the culmination of the entire process. Here, from wood and glue, a plywood sheet is born, ready for battle. Coming out of the press, the sheet is still hot. It is laid on a cooling conveyor, a wind tunnel where cold air draws off the residual heat. Then, a sanding machine. On both sides, large rollers with sandpaper remove microns of irregularities, even out the surface, remove excess glue. Next, cutting into standard formats, usually 4 by 8 feet, although a customer can request 6 by 10 feet, or even mini sheets. Then, quality control, scanning, marking, packaging. Each sheet is marked with a code, a grade stamp, a production date. It is packed in stacks of 40 to 60 pieces, wrapped in stretch film, and off to the warehouses. Each sheet that leaves the factory has passed through water, steam, blades, fire, a press, and saws. And now it can be anything. It becomes a wall in a new house in Kansas, or the back of a chair in a New York coffee shop. Sometimes, the level of a stage in a music school in Iowa. Another time, the roof of a house in Mississippi, the floor of a trailer somewhere in the middle of Arizona, or even the body of a truck speeding down I-80 at night. And each time, thousands of layers of wood hold together, as if whispering, "We are plywood. We are stronger than we look." What made of plywood is right next to you right now? Every year, over 50,000 tons of neodymium magnets are produced worldwide. Without them, electric cars, smartphones, and even rockets wouldn't work. But few people know that it all begins with dirty ore, mined at depths of hundreds of feet. To turn it into a super powerful magnet, it must go through more than 10 complex stages, where every second and every degree matters. There's a moment where the material explodes from within. Why? If you watch until the end, you'll discover a technological secret that even the world's largest manufacturers keep hidden. The mining and primary processing of rare earth ores are a key stage in the production of neodymium magnets, as this is where the foundation for obtaining the necessary components is laid. This process begins with the large-scale mining of ore containing rare earth elements, which are part of neodymium. In the first stage, the ore is extracted from the Earth's crust using various mining methods. This can be either open-pit mining or underground mining, depending on the depth and type of deposit. After extraction, large pieces of ore are delivered to crushing plants. At the crushing plants, the ore undergoes primary crushing. Large boulders of ore pass through a series of crushers that gradually reduce their size to smaller fractions. This is necessary for further effective processing and extraction of valuable components. The crushed ore may then be fed to mills, where further fine grinding takes place to a powder or pulp state, consisting of fine ore particles suspended in water. The next critically important stage is ore beneficiation, the goal of which is to separate the rare earth minerals from the gangue. This process can include various methods. One of the most common methods is froth flotation, where the crushed ore is mixed with water and special reagents. These reagents selectively attach to the surface of the rare earth minerals, making them water repellent. Air is bubbled through the mixture, creating bubbles to which the hydrophobic minerals adhere and rise to the surface, forming a foam that is then collected. Heavier particles settle faster, allowing them to be separated from lighter ones. Some rare earth minerals have magnetic properties, which allows them to be separated from non-magnetic components using magnetic separators. After beneficiation, a concentrate is obtained, which contains a much higher concentration of rare earth elements. However, this concentrate is still not pure metal. It requires further chemical processing, which usually includes dissolving valuable components with acids or alkalis, precipitation, solvent extraction, and ion exchange chromatography. These processes allow for the individual separation of each rare earth element and its purification to a high degree. For example, neodymium is separated from other rare earth elements such as praseodymium or samarium. The final result of this complex chain of processes is obtaining high-purity neodymium oxide, which is then reduced to metallic neodymium. This metallic neodymium, in the form of granules or ingots, is ready for the next stage, alloying with other components to create powerful neodymium magnets. The entire process requires strict quality control and significant energy expenditure, but is absolutely necessary for obtaining the raw material for the production of these strategically important materials. After the careful extraction and purification of rare earth elements, particularly neodymium, comes one of the most important stages in the production of high-performance neodymium magnets: alloying. This process requires extreme precision and control, as the final microstructure and, consequently, the magnetic properties of the finished material depend on it. The purified metals, neodymium, iron, and boron, are carefully weighed in strict proportions. These three elements are the main components of the alloy that provides unique magnetic characteristics. In addition to them, small amounts of other elements, such as dysprosium, terbium, cobalt, or copper, may be added to the alloy. These additives are introduced to achieve specific properties, for example, to increase the magnet's thermal stability, improve resistance to demagnetization, or modify the material's brittleness. The exact composition of the alloy is a trade secret of many manufacturers and varies depending on the desired final characteristics of the magnet. The weighed components are placed in a specialized vacuum induction furnace. The use of a vacuum is critically important, as it prevents the oxidation of rare earth metals and other components at high temperatures. Oxidation would lead to the formation of undesirable phases, which would worsen the material's magnetic properties. Induction heating ensures rapid and uniform melting of all components, creating a homogeneous melt. The melting temperature in such a furnace can reach over 2,700 degrees Fahrenheit. After achieving complete melting and homogenization of the alloy, the stage of rapid cooling begins, known as the strip casting method. This is a key moment for forming the optimal microstructure. The molten metal is poured in a thin stream onto a rapidly rotating cooled drum. Contact with the cold surface of the drum leads to extremely rapid cooling of the melt, at a rate of up to millions of degrees per second. Such extremely rapid cooling prevents the formation of large crystalline grains and allows for the formation of an amorphous or microcrystalline structure. Instead of the typical crystalline structures formed during slow cooling, extremely fine grains are formed. This process is also known as rapid solidification, and it is fundamental to achieving high magnetic properties. The resulting material has the form of thin flakes or ribbons that are easily crumbled. This unique microstructure, with very fine, often anisotropic grains, is the key to the high strength of neodymium magnets. The smaller the grain size, the more difficult it is for magnetic domains to change their orientation, which provides high resistance to external demagnetizing fields. Thus, the alloying and rapid cooling stage is fundamental for forming the magnetic characteristics that will later be fixed in the subsequent stages of production. After the alloying and rapid cooling stage, when thin flakes or ribbons of the neodymium iron-boron alloy have been formed, the stage called hydrogen decrepitation begins. This is an innovative and highly effective method used for the primary crushing of the obtained material before further fine milling. The essence of the process lies in the interaction of hydrogen with certain components of the alloy, particularly with neodymium. Neodymium, being a rare earth metal, has a high chemical affinity for hydrogen and is capable of forming hydrides. When the alloy flakes or ribbons are placed in a controlled environment where they are exposed to gaseous hydrogen, the hydrogen begins to penetrate the material's structure. The penetration of hydrogen atoms into the crystal lattice of neodymium and the formation of hydrides leads to a significant expansion of the volume of the crystalline grains. This expansion creates enormous internal stress within the material. Since the alloy is already relatively brittle, these internal stresses lead to the formation of numerous microcracks along the grain boundaries and within them. As a result, the material becomes extremely brittle and literally breaks down into small particles that are much smaller than the original flakes. This process occurs without the use of mechanical grinding, which avoids significant contamination of the material from mill elements and reduces energy costs. In addition, hydrogen decrepitation occurs mainly along the grain boundaries, which ensures the preservation of the magnetic properties of individual grains that were already formed during the rapid cooling stage. The powder obtained after hydrogen decrepitation is an intermediate link in the production of neodymium magnets. It is not yet fine enough for pressing and sintering, but it already has a much smaller size, which makes the next stage, jet milling, more economically viable and technologically manageable. This stage demonstrates how the chemical properties of elements are used to optimize physical processes in metallurgy. The powder is pressed into a solid block in a vacuum under a strong magnetic field. This field orients the grains so that their magnetic domains are aligned in the desired direction. The block is immersed in a cold, isostatic press under high pressure to remove residual air gaps. The pressed block is placed in a furnace at a very high temperature, over 2000 degrees Fahrenheit, just below the metal's melting point. This process allows the blocks to achieve full density and develop their magnetic and mechanical properties. After sintering, the blocks are reheat treated at lower temperatures to relieve internal stresses. The resulting magnets are cut and ground to the desired shape. Due to the high cost of the material, waste is minimized. Most neodymium magnets are coated with a protective layer, usually nickel-copper-nickel, to prevent corrosion. At this stage, the magnets have a preferred direction of magnetization, but are not yet magnetized. They are placed in a fixture that briefly exposes the magnet to a very strong magnetic field. After the field is removed, the magnetic field remains in the magnet. Imagine a single chain link weighing 500 pounds and almost 4 feet long. Now, hundreds of such links connected together, stretching for 1,000 feet and weighing tens of tons. This isn't a movie set for a film about titans. This is the anchor chain of a supertanker, capable of holding a vessel the size of a skyscraper in a stormy sea. These giants of marine engineering don't work in the quiet of a harbor, but in the harshest conditions on the planet, under insane weight, with temperature fluctuations from -40 degrees Fahrenheit to positive 120 degrees, in salt water that eats away even the strongest steel. The first and most important step in producing anchor chains is choosing the right steel. For chains that must withstand tremendous tension in the open sea, low alloy structural steel with increased strength, impact resistance, and corrosion resistance is used. Its composition is selected so that the chain doesn't break from metal fatigue, isn't eaten away by salt, and doesn't crack from temperature fluctuations. Factories receive steel in the form of solid rods or square bars, which look like long metal beams. Their diameter usually ranges from 3 to 6 inches, and their length up to 10 feet. The weight of one such piece is hundreds of pounds. All of this is stored in open assembly yards or inside large metal hangars because the parts can withstand any weather conditions. Before being fed into production, the steel is checked for purity of composition. Even minor impurities can make the metal brittle. After quality inspection, the steel heads to the cutting lines. These are long automated sections where massive rods are transformed into blanks for links. Each steel rod is picked up by a hydraulic manipulator and placed on a guide. Then the main hero of this stage comes into play: a hydraulic guillotine press, or a cutting saw with carbide discs. The device calibrates the length, and when the blank is in the correct position, it presses with a force of thousands of pounds per square inch. With each loud thud, a characteristic crunch is heard, and a piece about 3 feet long is separated from the rod. This piece will become one link of the future anchor chain. A counter is displayed on a special screen or directly on the machine's body. It tracks how many links have already been prepared and whether the length needs to be adjusted. Each cut piece falls onto a conveyor or into a basket, where it is automatically checked by a laser scanner. If the system detects a deviation in length or an uneven end, that piece is sent back for remelting or trimming. The pieces that pass inspection are moved on to heating furnaces, where a bright orange heat of over 2000 degrees Fahrenheit awaits them. This temperature allows the steel to soften without losing its structural properties. It is there that the steel will become pliable and ready for bending into links. The cut pieces of steel, incredibly thick, rough, and heavy, are still cold, so they can't be bent at all. To give them the shape of a link, they need to be made pliable. The blanks are fed onto a roller line that leads directly into an induction or gas furnace. Inside the furnace, a dull hum can be heard, and the air is heavy, hot, and saturated with a metallic smell. The blanks lie on stands or are suspended on special rods and are gradually heated for 20 or 30 minutes. Externally, they begin to glow, first cherry red, then orange, and finally almost white. This is a visual indicator. The steel piece is ready for forming. As soon as the piece reaches the required temperature, it is quickly removed by a robot or a worker in a heat-resistant suit, because there's no time to waste. Steel loses heat very quickly, and if it cools by even 200 or 300 degrees, it will no longer be bendable. That's why the logistics of the hot chain production are so well coordinated. Every second matters. As soon as the 2000 degree Fahrenheit blank is removed from the furnace, it is instantly transferred to a bending machine, which looks like a hydraulic press robot with metal arms. These units can easily manipulate pieces weighing several hundred pounds, rotating, securing, and bending them with surgical precision. The essence of the process is simple at first glance. The blank is clamped between two massive forming rollers, one of which rotates around an axis. At the same time, the other presses with a force measured in tens of thousands of pounds per square inch. The steel yields and smoothly bends, forming a perfect ring with a diameter of up to 4 feet. While the metal is still soft, the ends of the link are joined, leaving the joint area slightly overlapped. Then the link is transferred to a welding station, where gas-shielded arc welding automatically begins. The temperature, over 5,000 degrees. The electric arc literally melts the edges and stitches them into one hole. The finished link is almost a part of the anchor chain, but before it is connected to others, the seam must be ground, heat-treated, and checked for defects. And only after this does it become part of a chain capable of holding a supertanker weighing hundreds of thousands of tons in a rough sea. While the link is still hot and pliable, it is immediately connected to the previous one, threaded through the already finished link. Only after this is the link closed, the seam welded, and this entire dual unit undergoes further processing. After all, it's impossible to open the previous link without damage, which would affect the chain's strength. When a link is welded, a noticeable seam remains at the joint, a bit rough, with weld spatter and metal buildups. In this state, it won't pass any tests, as it could catch on other links or even become a weak point under pressure. So, grinding comes into play. On a huge table, Similar to a workbench for airplanes, lies a link weighing under 300 pounds. It is secured so that the seam is clearly accessible. An abrasive machine or an operator with a powerful grinding tool gets to work, which roars, sparks, and makes a characteristic buzz sound. The goal is to smooth the seam as much as possible, remove microcracks and excess metal without damaging the main structure. Grinding takes place in several stages: first coarse, then medium, and finally, polishing. For this, discs of different grits are used, from 24 to 120, and sometimes even higher. After grinding, the link is blown with compressed air, cleaned of dust, and at this stage, it already looks like a perfect ring. But an external shine is not yet a guarantee of strength. So next comes heat treatment. Heat treatment strengthens the metal structure and makes the chain capable of withstanding insane loads in the depths of the sea. This is a complex series of thermal processes that are carefully controlled. First, the links are heated in furnaces to a temperature of 1,700 degrees Fahrenheit. Huge chambers, resembling metallurgical tunnels, hold dozens of links at once. Here, it is important to achieve uniform heating throughout the thickness of the metal, so that no internal stresses arise that could cause microcracks. Next comes quenching. The links are rapidly cooled, usually in baths of oil, water, or a special salt solution. It is this temperature jump, from red hot to cold, that creates a hardened crystal structure in the steel. The result is increased hardness and wear resistance. But after quenching, the metal becomes too brittle. So the next stage is tempering. The links are placed back in the furnace, but at lower temperatures, approximately 1,000 degrees Fahrenheit, and held there for several hours. This allows residual stresses to be relieved, restoring elasticity and a balance between hardness and strength. Sometimes induction hardening is used, where heating occurs locally, only in the areas that experience the greatest loads. For example, the inner surfaces of the link where it connects with others. After heat treatment, the links are coated with an anti-corrosion layer that protects the metal from salt water, moisture, and rust. This is usually a hot dip galvanized coating, or epoxy paints, applied by dipping or spraying. Before this, the surface is degreased and ground again. The coating must lie evenly on every indentation, because the durability and safety of the entire structure depend on this. Imagine a giant factory where copper and aluminum, like two ancient titans, come together in a single dance of heat. The air here vibrates with precision. Coils spin at a speed that could twist time, and furnaces burn brighter than a sunset over the Sahara. Every hour, this mega complex produces hundreds of heat exchangers, the heart of every air conditioning system, refrigerator, or car. It all begins with the gleam of metal. Ready for a deep dive? Then let's head into the very core of production. To start manufacturing, we need to prepare the materials. Copper tubes are made from high-quality copper, often with internal spirals or microfin structures to improve turbulence and heat transfer. Before further processing, the tubes undergo cleaning and annealing to relieve internal stress. Aluminum fins are cut from aluminum alloys, such as 8006 or 1199, which have excellent thermal conductivity and corrosion resistance. The fins can have various shapes: straight, wavy, perforated, to optimize airflow and heat transfer. At large factories, especially in Asia, the United States, or Europe, where heat exchanger production is large-scale and automated, material preparation is part of the same complex. There are workshops that uncoil large spools of copper or aluminum wire, cut plates and tubes to the required length, surface treat them, and store the semi-finished products under controlled humidity and temperature conditions. In smaller production facilities, or in cases of clear specialization, for example, heat exchangers for aviation or military equipment, the blanks may be supplied already prepared from outside. This helps reduce equipment costs and allows focusing on precise assembly and testing. In a huge workshop, where only the rustle of metal and the precise clicking of mechanisms can be heard, the mystery of creating the heart of a heat exchanger, its core, begins. Thin aluminum fins, like metal scales, light, flexible, but with character, are fed onto the conveyor with millimeter precision. They have a complex geometry, corrugated, with microscopic slits that increase the heat exchange surface area, like a fan catching every breath of air. In parallel, from another line, copper tubes slowly slide down. Short, but very important segments, shiny after cleaning, strong and plastic at the same time. Their diameter is precisely matched to the fins. Each tube must pass through a series of holes in the fins, literally piercing the entire stack, like a thread gathering beads. This is done manually only in experimental production or in the early stages of development, but in most factories, this stage is fully automated. After stringing, mechanical expansion begins, a unique procedure where special mandrels are inserted into the tubes, or they are pressed from the inside with hydraulics. This expands the copper, and it presses tightly against the holes in the fins. The contact must not just be tight, it must be perfectly tight, because this is the area where heat will be transferred from the hot fluid to the cooling air or vice versa. Every microcrack is a loss of efficiency. In more complex or critical models, the tubes are also brazed to the fins, either in a furnace or by the induction method. The metal melts only on the surface, merging the aluminum and copper into a single structure. The assembled structure is inserted into a frame. On the sides, strong aluminum or steel supports, top and bottom, collectors that will gather and distribute the heat transfer fluid. This is now the core, which will undergo dozens more checks before it ends up in an air conditioner, car, or server cooler. When the core is assembled, a real test awaits it: brazing. First, the structure is prepared, cleaned of oils and contaminants left during assembly. This is done with special degreasers or washing solutions, because any particle of dirt is a potential enemy of quality connection. Then, a filler metal is applied to the brazing spots, a thin layer of alloy, most often aluminum or copper, which melts before the base metal. And here, the key moment: the furnace. Large, sealed like a vacuum capsule, it slowly swallows the blanks. Inside, an oxygen-free atmosphere, often with nitrogen or argon, to avoid oxidation. The temperature rises gradually to avoid creating stress in the metal. At its maximum, about 1,112 degrees Fahrenheit for aluminum, the filler metal begins to flow, but not boil. It fills the gaps, like liquid gold, penetrates the smallest crevices between the tubes and fins, binding everything together, like lava squeezing mountain rocks into a single block. This process is called diffusion brazing, extremely precise and uniform. The furnace can hold dozens or even hundreds of heat exchangers at a time, so each one undergoes processing under absolutely identical conditions. This guarantees stability, no overheating, no underbrazing, and it's also economically viable. After leaving the furnace, the structures shine like newly forged artifacts. Externally, nothing has changed, but inside, a transformation at the molecular level. This is no longer a set of parts, but a single body capable of withstanding years of operation, temperature changes, impacts, vibrations, and aggressive environments. While the heat exchangers are still hot, they are slowly cooled in a controlled environment. This is not just a technical procedure, it's a hardening ritual. If cooled too quickly, the metal structure will develop microcracks. If slowly, without control, the geometry will be compromised. So, after the fire comes water. After the insane temperature when the solder flowed between the aluminum and copper, the heat exchanger seems to take a breath. It has survived the hottest moment of its life. But ahead lies an equally responsible stage: cleaning, inspection, protection. First, the heat exchanger enters a washing zone. Here, the remnants of flux, the substance that helped the solder flow evenly and tightly, are washed off. If left, it could later cause corrosion or reduce the device's efficiency. Therefore, the part is bathed in special tanks, hot water, neutral solutions, sometimes ultrasonic cleaning, everything to make every millimeter shine with cleanliness. But beauty is not everything. Each heat exchanger is tested for leaks. Imagine air hoses being connected to it, submerging it in water, and applying pressure. Even a tiny bubble means a problem. Either a joint wasn't properly brazed, or a microcrack has formed, and then it's off for reprocessing. But if the water remains calm as a mirror, the product moves on. Strength is also checked by pressure, often higher than what the product will withstand in real conditions. After this, the final cosmetics. Aluminum elements may be anodized. This is an electrochemical process that creates an oxide film on the surface. It makes the material resistant to rust and adds an elegant matte sheen. Sometimes special protective coatings are applied, varnish or polymer paint, which not only adds color, but also protects against aggressive environments. The world is changing, and heat exchangers are changing with it. While classic copper tubes and aluminum fins still serve faithfully, new heroes are appearing on the horizon, with the strange gleam of future technologies. One such breakthrough is aluminum-clad copper tubes. Imagine this: lightweight and corrosion-resistant aluminum. On the outside and inside, a copper heart that conducts heat with incredible efficiency. This combination preserves the key advantages of both metals, minimizing their weaknesses. These tubes, like a perfect union of opposites working in harmony. They are easy to process, lighter than pure copper, cheaper, and yet provide thermal efficiency on par with top-tier solutions. But the brightest future belongs to 3D printing. In sterile laboratories, where printers don't apply ink but molten metal, structures are born that previously existed only in the fantasies of engineers. Here, they don't just copy familiar tubes and fins, they create new geometries, spirals, lattices, organic forms that mimic the microstructures of bones or leaves. They are lighter, more efficient, more compact, and they can be tailored to a specific device or operating condition down to the smallest detail. These printers can work with copper, stainless steel, and eventually, new generation composites. Such products cool processes faster, transfer heat more efficiently in electric vehicles, and last longer in harsh climatic conditions. And all this with fewer resource costs and minimal heat loss. Every second globally, over 3 billion gigabytes of data are transmitted. But did you know that all this happens thanks to a thread thinner than a human hair? And that this thread starts with ordinary sand. Not beach sand, but perfectly pure quartz, where there's only one impurity per million parts. To create fiber optic cable that transmits light at a speed exceeding 300,000 kilometers per second, you have to go through a journey involving chemical vapors, sterile laboratories, a 2,500-degree furnace, and lasers that monitor every microcrack. This process looks more like manufacturing a spaceship than a cable, but it is the foundation of the internet you are using right now. To create a thread capable of transmitting light at a speed exceeding 186,000 miles per second, you have to start with sand. But not just any sand, only special, extremely pure quartz sand, where the main substance is silicon dioxide. For fiber optic production, sand with a silica content of over 99.9% is used, meaning in 1 million parts, there's only 1 part of impurities. Imagine this: in every pound of raw material, no more than a few millionths of an ounce of impurities. And this is critical, because even 1 billionth of an inch of foreign metal or organic matter can cause light scattering or absorption in the fiber optic cable. And then the signal, which was supposed to travel 60 miles without amplification, simply disappears. Raw material for fiber optic cable isn't just washed or filtered, it's purified at the molecular level. Manufacturers often use vapor phase chemistry. Quartz sand is converted into gaseous silicon tetrachloride, which is then distilled, filtered, and deposited as pure vapor. And only then is it converted back into glass. Add to this strict control of temperature, humidity, air currents in clean rooms, and you'll get an idea of how far this is from an ordinary sandy beach. Production laboratories look more like National Aeronautics and Space Administration sterile zones than a glass workshop. And all for the sake of ensuring there's not a single defect in every yard of the future fiber. Because when you're transmitting light over thousands of miles, even one microscratch can cost you signal quality. A large transparent glass cylinder that will later be melted and drawn into a very thin thread. This is the fiber optic preform. This huge glass rod is made using a method called vapor deposition. In a large furnace, air is mixed with very pure gases. These are different substances that turn into vapor when heated. These vapors hit the inner surface of a transparent tube, which is heated very intensely. When the vapors touch the hot wall of the tube, they deposit and turn into tiny droplets of glass, like dew collecting on leaves in the morning. Gradually, these droplets collect, layer by layer, until a thick layer of glass forms inside the tube. Then this tube is heated even more intensely, and it collapses into a dense solid rod. And this is our preform. The preform is placed in a special furnace that heats up very intensely. The temperature inside it reaches approximately 4,700 degrees Fahrenheit. This temperature is so high that the glass becomes soft and starts to melt, like caramel on a stove. When the end of the preform melts, a drop of molten glass begins to drip from it. This drop is very carefully drawn downwards, and a thin thread is formed from it. This thread, the optical fiber, is drawn at a speed of approximately 1,000 feet per minute. Imagine that. It's faster than a cyclist moving through the city. It's important for the thread to be of uniform thickness throughout its length. The thickness of an optical fiber is usually around 125 microns, or approximately 0.005 inches. That's very, very thin. For comparison, the average human hair is about 100 microns thick or less. To keep this diameter under control, special instruments are used during the process. They look at the thread in real time and measure its thickness. If the thread starts to become thicker or thinner, the system automatically changes the drawing speed or the furnace temperature to correct it. After the optical fiber has been drawn from the preform and has become a thin, transparent thread, it needs to be protected. The fiber is very thin and fragile. If left unprotected, it can easily break, cracks will appear, or dirt will get on it. Therefore, immediately after drawing, the fiber is coated with a special protective layer. A thin thread is pulled from the furnace. After the furnace, the thread immediately goes into a coating machine. This is a special device that clothes the thread in a plastic sheath. The optical fiber enters a special part of the machine called the coating head. It's like a small tube or nozzle, inside which there's molten protective material. As the fiber passes through this tube, a layer of liquid polymer is evenly applied to it. The polymer has very low viscosity, so that the coating is thin and even, but dense enough to protect the fiber. This coating layer usually consists of two parts. The primary coating is a very soft, elastic layer that dampens mechanical shocks and allows the fiber to bend. The secondary coating is harder and more rigid, protecting against external influences, dust, and scratches. These two layers are applied sequentially, one after the other, to provide reliable protection. After applying the liquid coating, the coated fiber passes through special forming rollers. They regulate the thickness and evenness of the layer, pressing the coating uniformly along the entire length of the fiber. These rollers are very precisely calibrated so that the layer is not too thick or thin. After the polymer has been applied and shaped, the fiber passes through a zone of ultraviolet light. Here, the polymer instantly hardens under the influence of ultraviolet lamps. This is a process called polymerization. Anyone who gets their nails done knows how this happens. Ultraviolet lamps emit light of a specific wavelength that activates chemical reactions in the polymer. Thanks to this, the coating quickly becomes solid, while retaining its elasticity and ability to protect the fiber. This is a very fast process. The coating solidifies in fractions of a second, literally. This method does not heat the fiber, so it doesn't damage it. This provides very strong and durable protection. The entire machine is equipped with sensors and control systems. They constantly measure the coating thickness, fiber feed speed, and uniformity of application. If the coating layer is too thin or there are defects, the system either stops the process or adjusts the parameters to avoid defects. At the end of all this technological magic, a spooling module, rotating with a hum resembling the sound of a jet engine, only in miniature. The fiber, like transparent silk, lies down smoothly and precisely, coil after coil. It shimmers in the light of the lamps, reflecting cold blue and white hues. the spool moves smoothly, to the left, then to the right, with millimeter precision, as if an artist is painting pictures with movement. One wrong angle, and everything will go haywire. So the system automatically adjusts the rotation speed and fiber tension with surgical precision. Around are sensors, lasers, cameras. They carefully ensure that the fiber lies flat, doesn't twist, and doesn't create tension. With every minute, more and more layers appear on the spool. Imagine, in a few hours, there are already several feet of thin, almost invisible fiber there. And all this, without a single break, without a single scratch. Because even a microcrack, and the light signal will get messed up, like a radio wave in a storm. Before cable assembly begins, the fiber from the spool is carefully wound onto a production line. Since one cable usually contains several fibers, individual threads are combined into ribbons or modules. For ribbons, the fibers are arranged parallel in a single plane, for example, 12 pieces, and glued together with a special resin. This makes them easier to work with during connection. For bundles, the fibers are twisted into a spiral strand and placed in a plastic tube. These ribbons or bundles are then placed into buffer tubes, thin, flexible plastic channels that provide space for the fiber's slight movements. This is important because when the cable's temperature changes or it's bent, the fiber slightly expands or contracts, and the buffer tube helps prevent it from being damaged. A gel that repels water and absorbs vibrations can also be added inside these tubes. Around the buffer tubes, strengthening elements are added. Fiberglass or Kevlar, very strong threads that protect the cable from stretching. Metal wire, for additional mechanical strength or grounding. A central strength member, a rigid element in the center that maintains the cable's shape. These reinforcements are needed so the cable can withstand tension, impacts, bending, and remain intact for decades. All of this is wrapped in an outer jacket. This is a dense plastic or polyethylene pipe resistant to ultraviolet light, moisture, rodents, temperature fluctuations. The cable is tested. The bandwidth of each fiber is checked, as is its bending strength and resistance to moisture. Then it's wound onto large drums, marked, and technical documents are added, and it's ready for transportation and installation.